Hello, this is Math 145, Section 4.3. And what we're going to do here is called the coefficient of determination, which sounds very fancy, but really it is just a derivation from our value of R, the correlation coefficient, and a pretty simple one. So we've got a pretty quick example here, and it comes back to our car weight and gas mileage data that we worked with before. So again, just to kind of review yourself, you've got a bunch of cars here and their weights and gas mileages, and of course I made a scatter plot of that. You will recall that in the last section we found the least squares regression line to be that craziness. Remember, in that equation, x represents the weight of the car and y hat represents the gas mileage. Just take a second, pause me down, and take a second and answer that question in the thought bubble. Which is the explanatory and which is the response variable? So what I said was that I thought the weight was influencing the gas mileage of these cars. And so I ended up with the explanatory variable being the weight and the response variable being the gas mileage. Now, you'll also recall that we found R, the correlation coefficient, to be negative 0.84158, which remember kind of, that's a terrible line, but we'll have to do. That was negative because the regression line sloped downward from left to right, and it was also pretty darn close to -1, which meant the correlation between weight and gas mileage was pretty darn good. Now, you'll also remember that the calculator gives you an R squared value, and answering the question, what is that, is the whole point of this section. So we know that as the weight of the car increases, the gas mileage decreases. And our regression line shows that relationship, right? But how well does that relationship really predict gas mileage? This value of R squared is going to measure how well the regression line describes that relationship between the explanatory and the response variables. Let's go to the next page and look at some actual numbers. All right, so we're going to look at a definition of the coefficient of determination at the top of page 2, and it really just says this R squared measures the proportion of total variation in the response variable that is explained by the least squares regression line. Okay, now we have some facts here. And the first one is that the R squared value has to be between 0 and 1. You might remember that R is between -1 and 1. So when you square a number between -1 and 1, you are going to get a number between 0 and 1. Okay, second, we have the fact that if R squared equals 0, the line has no explanatory value. You might remember we talked a little bit about the correlation coefficient. R being 0 meant that the regression really wasn't there. There was no relationship. There was no linear relationship, at least. So if our little r is 0, well, then that would make R squared 0 as well, right? Basically, it means there's no linear relationship between the two variables. And then, again, very similar to when we talked about how if the R value was close to -1 or 1, we said, hey, there's a really strong linear relationship. Here we have the third fact there. The closer R squared is to 1, the better the line describes how changes in the explanatory variable affect the value of the response variable. And then lastly, if R squared is equal to 1 exactly, and of course in real life this doesn't happen much, but if it does, that means the line explains 100% of the variation in that response variable. Okay, so let's try out a problem. This is just number 1. Why don't you read that over and try to fill in that little answer spot there, and also maybe think about that thought bubble down there. Pause me down, do that one real quick, and then start me back up. All right, so what do we have? We have the value for R squared for this example is 0.708, and literally I just took this guy here and squared it, and I got that. All right, now I turn that into a percent, So I'm going to take my decimal point over, right? 2 places, donk, donk, and we get 70.8%, and that's going to go here. Now, what we're really saying, what this is all about, is that 70.8% of the variation in the gas mileage, right, how those numbers varied through the table, could be explained by our regression line. So our regression line's doing a pretty good job about showing the relationship between weight and gas mileage. By the way, the book does point out there is kind of a technical difference between lowercase r squared and capital R squared. You might have noticed I changed case there between this and the last section. Don't worry about it. For our purposes, we're just going to say they're interchangeable. Now, on to this last thought bubble here. Now, if you think about the things that could cause your gas mileage in your car to vary, you've got things like, of course, weight of the vehicle, but you've also got things like driving habits and tire quality, right? You probably can think of a couple more things that would change your gas mileage. So what we're saying here, this R squared value, is that 70.8% of the variation we see in gas mileage is due to weight. But there's some more, and that's 100 minus 70.8%, or 29.2%, is due to other things. Let's go on to the next page, and we'll see where this section ends. This is an optional section, this whole page there. It's about the deviations. It kind of explains a little bit more detail, but it's absolutely optional. So if you want to stop now, feel free. For those of us who are carrying on, of course, we're going to use our same example. Now, gets a little wacky. So the mean value of the response variable, and remember, that was the gas mileage. The mean value was 20.1 miles per gallon. We're going to call that Y bar. This is really just the averages of the values given for gas mileage in the table. Now, think about just one particular car, the Dodge Dart, which had an observed gas mileage of 24 miles per gallon and a weight of 3,242 pounds. If you find this point on the graph, you can circle it. Go ahead, do that now. I'm just going to do it real quick like right there. And what we're going to do is we're going to compare our regression prediction against the observed value there, and against also the mean of the sample. Okay, so again, here's my Dodge Dart, and it had a X value of 3,242 pounds and a Y value of 24. So first thing I'm going to do is I'm going to subtract the observed value and the mean value for all of the gas mileages. And that would get 24 minus 20.1. That's 3.9 miles per gallon. This is called the total deviation, and you'll see it there marked on the little graph there. Okay. On the other hand, the least squares regression line, notice I'm using the y hat equation from page 1, and I put the X value, or the weight of the Dodge Dart, in there, and it would have predicted a gas mileage of 22.2. And you'll actually see this as a red dot on the graph. Now, if we subtract y hat minus the mean of all those gas mileages, we get 1.1 miles per gallon, and that is called the explained deviation, which you'll also see on my graph. Okay, finally, let's find the difference between the observed value, which is just the value given in the table for this Dodge Dart, and the predicted value of 22.2 miles. And you see my calculation there, 1.8 miles per gallon. And that is called the unexplained deviation, which again is right there in the little picture. So Why do they call it the total deviation? Well, it's because the total deviation equals the unexplained plus the explained deviation. Now, we really are not going to get into much more. The book does touch a little bit on these deviation stuff, so I thought I would throw that in here, but you're really not going to need it in a day-to-day kind of way. The last thing I'll say is this little paragraph, and it's kind of related to a couple of those facts at the top of the last page, and it basically says this. It can be shown that the closer the observed y values are to the regression line, and what we're talking about is, the observed y values are those from the table, right? The closer those are to the regression line itself, the larger r squared will be. In other words, the value of r squared will be closer to 1 if the points line up closer to a perfect line. And again, if you reread those facts at the top of page 2, you'll sort of see that. You could use this to estimate the value of r squared given a graph of points and their regression equation. But again, really that's just not going to come up for us this semester. Okay, so that's section 4.3. Thanks a lot for listening, and make sure you keep those questions coming. Okay, bye.